Okay, so I will now do the fundamental domain of a discrete group action. So let's say gamma is a group acting on X, and the X is you can say Hn or Euclidean space En or the spherical space Sn. But beyond that, this may not really work. Okay, so in like a complex hyperbolic space, it may not really work. So it's a peculiarity of these spaces these things work. So we don't have a theory yet for that. So fundamental domain for gamma is an open domain F, so that the GFX is a collection of disjoint sets, and their closures will cover X. So that's a definition of a fundamental domain. But of course, it can change from book to book here. So the fundamental domain is locally finite if the above closures are locally finite. Okay. So we of course need the locally finite in most cases. And the Dirichlet domain of U in X is an intersection of all the half spaces. So the points of X points. So you fix U, and then you look at all the elements GU. And you want to look at all the points which is closer to than U than any other image up here. So this is a nice condition, and then DU is a convex fundamental polyhedron. Okay, so you can verify that this Dirichlet domain, if you define it like this, is a fundamental polyhedron. Okay, of course, this is related to Delaunay division by some applied mathematics, which is also very useful. And also the regular octahedron is an example of a surface of genus 2. Is an example of Dirichlet domain with origin as U. Okay. So if you look at the hyperbolic surface of genus 2, then some cases you take U as the origin, and then you'll get a regular octahedron in some cases. So tessellation of X is a locally finite collection of polyhedra covering X with mutually disjoint interiors. And the convex fundamental polyhedron provides example of exact tessellations. And the P is a exact convex fundamental polyhedron of a discrete group of isometries acting on X. Then gamma is generated by the G gamma. P G gamma is a side of X. Okay, so using this idea, you can define side pairing and derive the Poincare fundamental polyhedron theorem. So given a side of exact convex fundamental polyhedron domain P, there is a unique element at GS, so that the P is equal to GSP. So so any side is an intersection of two polyhedron images, one itself and the image. So each side will be this, and then S, you can write S prime to be the image of under S GS also. Okay, so that will be a side, because if you put GS inverse here, then you get GS inverse P intersect P. So it will be another side of P. So in that sense, GS prime is GS inverse because of this property. Okay. So I should, yeah, there's a P missing here, P, okay. So gamma side pairing is a set of GS for a side S of P. So the equivalence class of P is generated by X equivalent to X prime if there's a side pairing sending X to X prime for X prime in P. So it will give you equivalence class of P of the boundary points of P only. And X is usually is going to be finite if it's locally finite fundamental domain, and x is going to be p intersect with the orbit of gamma x. Okay? So you can or verify that. And then you can obtain a cyclic relation. So S1 is, let's say S1 is a given S for a given side, and then you choose a side R of S1. That's R. So that will be side R of S1. S1 is a polytope, and then you obtain the S prime that meets S1 at R, and then S2 to be the side adjacent to. Sorry, S1 prime is the one which is equivalent to S on the side pairing, and then S2 to be the side adjacent to S prime, so that the S1 GS1 S1 prime S2 is going to be R. So the one the where it meets will be the R here. So you choose a side R, and then you obtain S1 prime, and then you get S2 prime, and so on. So by induction, you can do Si plus 1 be the side of P adjacent to S1 prime I, so that the GSI is GSI prime intersect GSI prime is the one Si minus 1 prime intersect the Si. Okay. So right, so that in this sequence you can keep obtaining these sequences of bases, sides, and then there's some integer so that this will come back to itself. Okay, after L it will be the same because there's only finitely many, and then this is a cyclic procedure. And then if you add up these angles between these sides, so these are the edges we chose, and then this angle has to be 2 pi divided by k in the case of a discrete group. And GS1, if you multiply the side pairings, and this is going to be order k. Okay, so that will give you some relation. So of course you can play with octahedron in the hyperbolic plane of genus 2, giving genus 2 surface. And so k is sometimes not the 1 because you could have orbifold points because there's a torsion element. Okay, but for manifold cases, k is always going to be just 1. So because I mean this has to be order 1 in the case of manifold. For order k you get a orbifold. This will be the deck transformation. Okay, so the period is number of side coming to a given side of codimension 2. So for each codimension 2 side, you get some sort of period. So these k will be different for each of these side. Okay. So so you can do this example yourself, that you start with A1D. So this is the A1 base A1 edge with the D vertex D, and then this will be identified the A1 prime this way, but because of the this is how you glue this, and then the A1 prime goes to A1 prime, but the D now corresponds to K, right? So you get this, and then you choose the adjacent one here, right? So this will be P1, it's K, so P1 K, P1 prime K, and then this is identified with P1 the orientation like this, so it goes to B, K goes to B, and then you choose A1 prime B like this, and then so on. So if you keep going, then you have to come back to itself eventually like this, and then that gives you all the identification in this case, but for some other polytope it might not. Okay, and anyway, so there are other examples. and then this will give you the relations of this. Okay, so Poincare fundamental theorem is the converse. So what I was showing was that if you have a tessellation like this, Dirichlet domain, then you get this relation. But the Poincare fundamental polyhedron theorem is that if you have a polyhedron with these sort of side pairings and the relations, then this will also give you a group. Okay, so that's a discrete group action. So if a polyhedron P with a side pairing asymmetry satisfying the above relation, then P is a fundamental domain of the discrete group generated by the side pairings. Okay, of course, if you have a discrete group, then you can find the generators and the relations using this by this theorem also. So if every K is 1, then the result is a manifold. Otherwise, we obtain orbifolds. Okay, and of course, the results are always complete if you do this kind of thing. And of course, I recommend looking at this kind of spaces. So they give you lots of examples of these kind of manifolds and gluings. So now we can also go to reflection group. So the discrete reflection group is a discrete group in G generated by reflections in X about size of the convex polyhedron. And you have to agree that the dihedral angles are always submultiples of pi, so pi divided by some integer. Then the side pairing is each side is glued to itself by the reflection of that side, so it just goes to itself. And then because of this submultiple condition, you get this relation, and this will generate a discrete group by the Poincare fundamental theorem. So you can look at the examples of Coxeter groups like this. So if the faces do not meet, then they don't have any relation, or the Kij is infinite. So for example, if a dodecahedron, regular dodecahedron with angles always pi divided by 2, then you get a fundamental reflection group. So actually this is from some other graphics related to this, so it's not really reflection group, but it has the same fundamental domain, and all these look same, but it has a different gluing though. So another nice example is triangle groups. So here you can find the triangle in X with angles some multiples of pi. Okay. Then we divide into two cases where pi divided by pi is bigger than sorry, this should be bigger than pi equal to pi and 0 to pi, not 0, sorry. So this is bigger than pi case again. So then these are all the cases. So this will be 2 to C. C can be any bigger than number bigger than C, and 2, 3, 3, 2, 3, 4, and then 2, 3, 5. So these are all the spherical Coxeter group in 2 dimension. And the first one is of course a dihedral group of order 4C, and then this one is it's just a symmetry group of tetrahedron, so it's a tetrahedral group, and then there will be symmetries of octahedron, and then the dodecahedron. Okay, or it could be the cube. It's symmetries of the cube, so they are dual. So, and 0 cases are these 3. So these are Euclidean ones. So first one is a regular fundamental triangle as a fundamental domain. This will have 2 right angles and so on. And the less than pi case will be there are infinitely many hyperbolic tessellation groups. So there are actually, okay, so for example, this will be hyperbolic, and then 2, 4, 3 triangle group. Okay, and this is even the ideal one, so you take ideal triangulation and then reflect. So this will just give you a free group, though it doesn't give you any. Okay. So for higher dimensional case, we look at three-dimensional case. Euclidean regular polytope, you expand it until you get achieve all the angles of pi over 3, then this will give you group. So you can obtain regular octahedron with angles pi over 2. So of course, in the Euclidean space doesn't have that angle, but you can expand it until you get these angles. And then there are some ideal polytope examples. As long as you get the edge angles to be submultiples of pi, then you get the reflection group. And so there are higher dimensional examples, and of course, he proved that there is no hyperbolic reflection groups of compact type above the dimension 30. So of course, there are some remaining questions which are very difficult questions, which I don't think has too much to do with theory, but some computations will be needed. And the final topic is a crystallographic groups. So I'll just briefly go through it. So crystallographic group is a discrete subgroup of rigid motions on Rn, and whose quotient space is compact. And the Beaver-Bach theorem is that the group is isomorphic to crystallographic group if and only if it contains a subgroup of finite index that is a free abelian rank equal to the dimension. So this is even translation groups. Okay, so you can verify that. And the crystallographic groups are isomorphic as abstract group if and only if they are conjugate by the affine transformation. Okay, so these are the classification according to Bieberbach. But so there are only finitely many crystallographic groups in each dimension, since since you have to extend the abelian group by some finite group, but this symmetry group can only be finite because you have to respect these lattices. Okay, so so for example, if you look at dimension 2, there are only 17 wallpaper groups. So in the dimension 2, it's called wallpaper groups. It's because it's a symmetry group of the wallpapers. Then there's 230 space groups for dimension 3. So this is a classical result, but Conway and Thurston proved it in here. But of course, in dimension 4, there might be much more, and then so on. But I think the one good thing about this is that this has a good approach using the orbifolds and so on. So that's yeah. Okay, so that's the end of this lecture here today, and